Good morning friends. Today we will discuss about the back bonding. What is back bonding? Back bonding is a type of coordinate bond having pi character. Back bonding is a type of coordinate bond having some pi character. Let's come to the example. BF3 molecule. BF3 molecule. If in between boron and fluorine only single bond would be there, then the bond length should be 1.52 angstrom. But in reality, actually the bond length is 1.30 angstrom. Instead of 1.52 angstrom, here the bond length is reduced to 1.30 angstrom. Why it is happening so? So let's draw the structure of boron trifluoride. In fluorine there are 3 lone pairs, but in boron there are vacant p orbital. Are you getting my point? Boron has the electronic configuration outermost orbit 2s2 2p1. Are you getting my point? So there are 3 outermost electrons. If we will count down it is not surrounding electron, it is not satisfying the octet rule 1 2 3 4 5 6. Okay, so it is also vacant p orbitals. So the filled p orbitals for fluorine has the filled p orbitals and it is the vacant p orbitals. So the electron pair present in the filled p f orbitals can donate these electron pairs towards the vacant p orbital of boron. So a type of back bonding takes place between fluorine and boron versus p pi back bonding. What I am saying? P pi back bonding, because the back bonding takes place between the p orbital of fluorine and p orbital of boron. So this is p pi back bondings. If we will draw all the equivalent structure of BF3, then it will be like this. From this fluorine, one case back bonding takes place. In the other case, the second fluorine takes place in the back bonding. In the third case, the last fluorine participate in the back bonding. So I can write the hybrid structure of boron trifluoride like this. Okay, you see, in between the boron and fluorine there is neither single bond nor double bond, it is in between, one single bond and one partial bond. So that's why here the bond length is 1.30 angstrom. Here the bond length is 1.30 angstroms. Okay, now we will consider some pair of molecules or ions in which in one case there back bonding is available, in other case there is no back bonding. So let's take the example. In example number 1, this is CCl3 minus ion and the other is CF3 minus ion. Among the two given examples, in which case back bonding takes place, we will see. Whenever back bonding takes place, one is the donor atom and one is the acceptor atom. In BF3 case, fluorine is the donor atom and boron is the acceptor atom. So the donor atom should have some lone pair and the acceptor atom should have some vacant orbital to accommodate the lone pair. So in C and chlorine, here carbon and fluorine, let's consider which one is the donor and which one is the acceptor. In carbon there is also lone pair due to the presence of negative charge, and in chlorine also there is lone pair. So who can donate the electrons? If we only consider the criteria of donating the electron pair, then this can also donate and this can also donate, but the other condition is the acceptor atom should have the vacant orbitals. No doubt in chlorine there is the presence of vacant orbitals, but in carbon there is no vacant orbital. You know the electronic configuration, it is 2s2 2p2. In excited state one electron will be promoted to the last 2p. So in there, but unfortunately in carbon there is no d orbital, that's why we can't say carbon has vacant orbital, okay, but chlorine has the vacant d orbital. So in this case back bonding takes place between carbon to chlorine, back bonding takes place between carbon to chlorine, okay. So here the lone pair present over carbon, so carbon is the donor atom and chlorine is the acceptor atom. By putting this same logic we can decide here carbon is the donor atom, it should donate the electron pair towards fluorine, but here also the same destiny, fluorine has no vacant orbital, so it cannot accommodate the electron pair, which is the fundamental criteria for the back bonding. So here no back bonding, here back bonding is not possible. So in this way you explain the two molecules, the two ions appears to be same, but in one case there is the presence of back bonding, in other case there is no back bonding. Now come to the example number 2. So this is one molecule. Now over the nitrogen there is one lone pair. Similarly the other molecule NSiS3, SiS3, SiS3. Here over nitrogen also there is one lone pair. So obviously if we will consider the two molecules, in both the case lone pair is available over nitrogen. So obviously it can donate the electron pair. So it is the donor atom, but here carbon is present and here silicon is present. Silicon has the vacant orbital, so it can acts as the acceptor atom. So here back bonding is possible, here back bonding is possible, here back bonding is possible, but in carbon has no vacant orbital, so that's why here back bonding is not possible. So we can say here no back bonding, but in case of this molecule there is back bonding. Are you getting my point? Now we will come to the example number 3. In example number 3 we will consider the case SiF4 and SiCl4. Are you getting my point? So here over fluorine and chlorine lone pairs are present. So obviously fluorine here acts as the donor atom and chlorine acts as the donor atom here. So in which case there is a presence of back bonding, in which case there is no back bonding, okay. So here silicon has the vacant orbital, because if you see the fourth group carbon, silicon, germanium, tin, lead, so it comes in the third period. So from the knowledge of quantum number we know silicon has the vacant orbital, so it can easily accommodate the electron pair from the fluorine. So here back bonding is possible. Similarly here chlorine can also donate the electron pairs towards silicon. But what is the point is there in when the concept of back bonding, we have to remember one very vital and fundamental things. Whenever the back bonding takes place between two, it is effective back bonding. When it is took place 2-3, back bonding is possible, that means little bit less. But when back bonding takes place between 3-3, this is not possible. So I am putting the tick mark here. 2-2 back bonding is possible, 2-3 back bonding is possible, but in 3-3 we can say there is no effective back bonding, so almost back bonding is absent in case of 3 and 3. So what do you mean by 2-2, 2-3 and 3-3? 2-2 means both the donor and acceptor atom belongs to the second period. 2-3 means one among that one donor and one acceptor, one belongs to second period, other belongs to third period. But whenever both the donor and acceptor atoms belongs to third period, at that time no back bonding is possible. Okay, so you look at the example SiCl4, silicon tetrachloride. In silicon also belongs to third period and chlorine also belongs to third period. So it has the lone pair available over chlorine, and silicon has also the vacant orbital to accommodate the lone pair from the chlorine, but both the atoms belongs to third period. So here though back bonding appears to be possible, but there is no effective back bonding, so we can say no back bonding. Are you getting my point? So here back bonding is possible and here there is no back bondings. Okay.